Hello everyone, welcome to this lecture number 6 of this topic, finite element and method. This is Mr. Suyog Patil, working as assistant professor in Department of Mechanical Engineering, Sharad Institute of Technology, College of Engineering, Yadrao, Ichalkaranji. Okay, so today we are going to see this numerical on the stepped bar. Okay, in the previous lecture we already discussed that one D bar element numerical. Okay, and now in this lecture we are going to see this numerical on the stepped bar. Okay, so this is an example which here it is given. So using the direct stiffness method, determine the nodal displacement of a stepped bar. Okay, determine the nodal displacement of this stepped bar as shown in the figure. Okay, now this stepped bar which is fixed at this end. Okay, and this bar stepped bar having a, this is first step having a length of the 50 mm, and this is the second step having a length of again 50 mm. Okay, the area of this first element, first part, it is a1. Okay, and Young's modulus of the material of this first part, it is first step, it is e1, capital E1. Okay, area of the second part, it is capital A2, cross sectional area. Okay, it is cross sectional area, and Young's modulus of this material of this second step, it is capital E2. Okay, then again where this force F2 is applied at this end, okay, at the free end, and this force F1 which is opposite to this force F2, which is applied at this node 2. Okay, at this point. Now here in this numerical, capital E1 and capital E2 are given, that is capital E1 Young's modulus of the material for this first step, it is given. This stepped bar, it is having two different materials. Okay, so E1 is given 200 gigapascal, E2 Young's modulus of the second step, this is given, okay, 70 gigapascal. Then area, cross sectional area of this first step, it is 150 mm square. A2, that is cross sectional area of this second step, it is 100 mm square, it is given. Okay, this force F1, opposite force, it is given 10 kilonewton, and this F2, okay, F2 at this free end, it is also given 5 kilonewton. Okay, 5 kilonewton force is there. Okay, these values are given here. Okay, so therefore this is the given things, given data. Length of the first element L1 is 50 mm, here it is L1 is equals to 50 mm. Length of the second element, it is L2 is equals to again 50 mm, same here L2 is equals to 50 mm. Okay, now we will solve this example by FEA method. Okay, so therefore first step in this example is we have to model a FE model. Okay, so therefore finite element model. So in that finite element model, in this numerical it is given use two element. Okay, so therefore for here we will use one element for this first step and second element for this second step. Okay, from this point to this second point, and from this to this fixed end we will use two elements. Okay, element for this one and second. So here this FE problem is modeled here, okay, by using this E1, that is element first, node 1 to node 2. Okay, and this is the second element for the second step. Okay, that is node 2 to node 3. Okay, so therefore this force acting at this node 3 is F3. Okay, force acting at the node 2 is F2. Okay, and force acting at node 1 is the F1. Okay, F1 is the force at node 1, and these are shown in towards this right side. Okay, because this x direction is given towards right side. Here we can see this x is given here towards right side, so therefore all these forces are taken here in the right side, F3, F2 and F1. Okay, but here F1 is given in towards left side here at the node 2. Okay, so therefore this value of this F1 will be minus. Okay, because it is whenever we are going to take in this example, F2 is equal to minus 10. Okay, so that we will see later. So first of all we have to prepare this model, FE model. Okay, and this is the first element having length L1 which is equals to 50 mm, and this is the second element, again it is having length L2 okay, which is again L2 is equals to 50 mm. Then again here Q1, Q2 and Q3 are the displacements. Okay, Q1 is the displacement at node 1, Q2 is the displacement at node 2 and Q3 is the displacement at node 3. Okay, these are the displacement values at the each nodes. Okay. Now second step in this problem is elemental stiffness matrix. Okay, preparation of this elemental stiffness matrix. So therefore the stiffness matrix for the bar element is given by, okay, as we previously discussed that this 1D bar element, for 1D bar element the stiffness matrix Ke is equals to A, capital AE, small then capital E divided by small le into 1 minus 1 minus 1 1. Okay, this is the stiffness matrix for the element. Okay, stiffness matrix for element. So therefore we have to calculate this K1 and K2. Okay, that means the stiffness matrix for this first element and stiffness matrix for this second element. Okay, first and second element K1 and K2. Now here, then for first element K1 is equals to A1 E1 divided by L1 into 1 minus 1 minus 1 1. Okay, so therefore we have to put this value of A1 here 150, it is already given in the numerical, then into E2, sorry E1, capital E1, that is 2 into 10 raised to 5 divided by L1, L1 is 50. Okay, by putting all these values and simplifying this equation, this matrix, so we will get this 10 raised to 5 into 6 minus 6 minus 6 6. Okay, here Q1 Q2 Q1 and Q2, this is this stiffness matrix for element, so elemental matrix for first element. Okay, then similarly second element, for second element it is K2 is equals to then E2 here A2 E2 divided by L2 into 1 minus 1 minus 1 1. Okay, but A1 A2 is given here, that is 100. Okay, area of the second element, cross sectional area. Then E2 it is given 70 gigapascal, so it is converted into 7 into 10 raised to 4. Okay, divided by L2 is 50. Okay, L2 is 50. So therefore again by simplifying this, so we will get this, it is equals to 10 raised to 5 into this matrix 1.4 minus 1.4 minus 1.4 1.4. Okay, and here the node values are Q2 Q3 Q2 and Q3. Okay, for second and third node, because element 2 is, for element 2 node 2 and node 3 are there. Okay, then after finding out this elemental stiffness matrix, we have to find the global stiffness matrix. Okay, global stiffness matrix for the entire numerical, entire problem. Okay, so therefore this global stiffness matrix for this stepped bar is given by K is equals to K1 plus K2. Okay, we have to add this elemental matrices. Okay, so therefore K is equals to K1 plus K2. Okay, so therefore here we can see this global stiffness matrix K is equals to, here already we have discussed this into previous lecture, that is Q11 Q21 Q31 then Q12, and here at this central node it will be Q22 plus Q22 of the second element. Okay, Q22 of the second element, then Q32, then Q13 Q23 and Q33. Okay, in this way, when we add this elemental matrix K1 and K2, okay, here 6 minus 6 0 minus 6 6 plus this 1.4 at this central node Q22 plus this Q22 of the second element, that means 6 plus this 1.6, so it will become 7.4. Okay, so therefore 6 minus 6 minus 6 6 plus 1.4, that is 7.4. Here it is minus 1.4 minus 1.4 1.4, and this is 0. Okay, Q31 Q13 and Q31 are 0 3. Okay, so therefore this is the global stiffness matrix. Okay, this is the global stiffness matrix. After finding out this global stiffness matrix, then we have to find the global displacement vector matrix and global load vector matrix. Okay, so therefore this global displacement vector matrix for the stepped bar is Q is equals to Q1 Q2 and Q3. Okay, Q1 means the displacement at node 1, q2 means displacement at the node 2, and q3 means displacement at the node 3. Okay, so therefore this q is the vector displacement, global nodal displacement vector. Okay, and then next, global load vector. Okay, the load f1, f2 and f3 are the loads at the nodes 1, 2 and 3 respectively. Okay, f1 means the load acting at the node 1, f2 means load acting at the node 2, and f3 means the load acting at the node 3. Okay, so therefore this load f1, load vector f1, f2 and f3. Okay, so therefore this value of the f1 is 0 here because it is fixed. Here we can see this value of the f1 at the node 1, it is 0 because there is no force acting at this node 1. This at this node 2, value of the f2 is here, it's something, it is f1, that is 10, and at node 3 it is f3, so it is 5 kilonewton. Okay, so therefore here f1 is equals to 0, f2 is equals to minus 10 into 10 raised to 3. Okay, it is because it is in the opposite direction, and f3 is equals to 5 into 10 raised to 3, it is in the along the x direction. Okay, it is along the x direction, so it is plus, and this is f2 is minus because it is in the opposite direction to the x direction. Okay, minus 10 into 10 raised to 3. Okay, this is the load vector. Okay, global load vector. Now equilibrium condition. Okay, equilibrium condition for this stepped bar is, so therefore this equilibrium condition is k into q is equals to f. Okay, k means the stiffness matrix, global stiffness matrix, q is the displacement matrix, and f is the load matrix. Okay, load vector. So therefore this k is global stiffness matrix is 10 raised to 5, 6 minus 6 0, minus 6 7.4, minus 1.4 0, minus 1.4 1.4. Okay, this is the k matrix. Then q means q1, q2 and q3. Okay, displacement matrix is equals to this load matrix, that is 0 minus 10 into 10 raised to 3, then 5 into 10 raised to 3. Okay, this is the load vector f. Okay, after preparation of this equilibrium condition and equilibrium equations, okay, then we have to apply boundary conditions. Okay, we have to apply the boundary conditions. So from figure, boundary conditions are q1 is equals to 0 because it is fixed. Okay, so here we can see at this end this bar is fixed. Okay, and this is the node number 1. Okay, node number 1, and this bar is fixed at this node number 1, so therefore displacement at the node 1 is 0. Okay, so here we can see the displacement at the node 1 is 0. That means this q1 is equals to 0. This is the boundary condition. Okay, so therefore we have to apply this boundary condition q1 is equals to 0 because it is fixed end. Okay, and after applying this boundary condition, we have to use this elimination method. Okay, elimination method of handling boundary condition. So therefore eliminating the corresponding row and column with respect to the 0 boundary condition. Okay, so here we can see when this q1 is equals to 0, when we put this q1 is equals to 0 here. Okay, in the elimination method we have to eliminate this row and this column. Okay, that means first row and first column of this uh, equation. Okay, so therefore after eliminating this we will get this matrix only. Okay, that means 7.4 minus 1.4 minus 1.4 1.4, q2 in q3 is equals to minus 10 into 10 raised to 3, 5 into 10 raised to 3. Okay, so we will get this matrix only. Okay, here we can see this is the matrix. Then again on simplifying, by simplifying these equations, that means 7.4 into q2 minus 1.4 into q3 is equals to minus 10 into 10 raised to 3. Okay, and second equation is 10 raised to 5 is common here, minus 1.4 q2 plus 1.4 into q3 is equals to this. Okay, so that means this first row, this column into is equals to this first value, second row into this column is equals to this second value. Okay, minus 1.4 q2 plus 1.4 times q3 is equals to 5 into 10 raised to 3. Okay, by simplifying these two equations, by solving these two equations, we will get these two unknowns. Okay, by simultaneously solving these equations q2 and q3. So therefore this value of Q2 is equals to minus 8.33 into 10 raised to minus 3 mm. Okay, and similarly value of Q3 is equals to 0.02738 into 10 raised to minus 3 mm. Okay, so these are the values of Q2 and Q3, displacement at node 2 and displacement at the node 3. Okay, so therefore this nodal displacement vector, so nodal displacement vector Q is equals to 0 minus 8.33 into 10 raised to minus 3, then minus 0.02738 into 10 raised to minus 3, this vector transpose. Okay, because this nodal displacement vector is vertical, okay, q1 q2 and q3, and it is written in horizontal, so therefore it is transpose here. Okay, so this is the answer of this nodal displacement vector. Friends, thanks for watching this video. If you like this video, please share, comment and like this video, then subscribe to my YouTube channel and click on the bell icon to get notified for more videos on this CAD/CAM subject. And thanks for watching. Thank you so much.